All right, so I may go ahead a minute or so early. I don't know how long I'll last through this, but um, let's start with free body diagrams. This section is in 3 dimensions as compared to the previous in 2 dimensions. So in the concept of free body diagrams, the concept is to eliminate eliminate a support and place the appropriate reaction there. So I'll let you go through the list here of all of the possible reactions, and I will be pausing the microphone occasionally in case I'm having a coughing problem. So here are some bearings of sometimes square bearings, things like that. All the different forces that can be carried by this. Notice now we have moments in here. This is basically due to the fact that we're operating now in 3 dimensions. And he gives some examples here. Free body diagrams are essentially the same thing as before. You're essentially taking the supports away. Okay, I push that. And you're replacing it with the equivalent load. Here's a typical example. You have these particular types, 2 types here. In this, the bearing can't take an axial load, nor can it take any particular moment. So he puts down what's sufficient. Now, actually, there are possibilities of having more reactions, but okay, here is a case in which, okay, so let's look at this end part. I mean, it's possible to have a moment this direction and a moment about that axis, but not one that will accept torque or a moment this way. So that's what you see. You see a moment here and you see a moment here. You don't see one that can spin around the Y. Here's a hinge per se. And if you go down through here, he just replaces the hinge itself. It's with the loads that it can carry. And the next part of this is actually equations of equilibrium. And that's this. Some of the forces, which actually there are 3 of those equations. And now there are 3 of these equations. Essentially, you got the sum of the forces about the x, about the y, and about the z. You got the sum of the moments about it. So you have 6 individual separate equations. When you were operating in 2 dimensions, you had 3 of these. You had the sum of the forces in the x, sum of the forces in the y, and the sum of the moments of the z. So you had 3 equations and 3 unknowns. Now you have 6 equations and 6 unknowns. Sometimes you won't need all 6. The most you have is 6. So this means you can handle up to 6 unknowns. But if you have a 7th unknown, yeah, you're indeterminate. Okay. So here's a 2-dimensional problem. You've got at the left end, You've got the moment at A, AX, and AY. And you got BX and C. I'm sorry, BY and CY. So you've got 1, 2, 3, 4, 5. However, there's nothing you can do. You don't have enough information here. If you took away one of these supports, you might have, but even then, you won't have enough. So this says the pipe assembly has 8 unknowns. There are only 6 equations. So here's a situation where you don't have enough equations. It's indeterminable, or indeterminate, as they say. There's improper constraints. Here's an improper constraint. For example, if you push here, that little roller is just going to allow B to fall through, and it's going to dangle. So there's not sufficient. Here's another one, 2 ball joints here and here. Put a load out here, let it loose, and basically the whole structure is going to basically fall vertical there. Here's a partial constraint. Here's the thing that what they're called partially constrained, but it's still improper. You get a roller bearing here, or roller ball, whatever. You push this way, the beam is just going to start moving to the right. This is another one. Technically, you'll know that this has a weight, and so it'll move to a certain point where it offsets that weight. But if it had no weight, there's no answer there. Okay, so let's go back and look at all right, let me get a drink and we'll just look at this example real quick and we'll do a problem. So here's the components of a reaction. Now this is a ball joint and a bearing. The bearing, more than likely, the ball joint can take a load in the X, Y, and a Z, but it can take a moment in no particular. Technically speaking, if you did a free body diagram here, let's take a good look at this thing. I contend that in addition to what he's got, that this thing could take a moment along here and a moment which if you were to draw this in a vector form, it would be so it could take a moment around that axis, and it could take one around that axis, meaning it can do that or do that. If we look back at the book, you'll see you'll end up with 6 equations. Okay, so some forces in the X, that'll get you nothing. Some forces in the Y, or here, he's summing the moments in the Y, about the Y. Now, thing about summing the moments about the Y is there was nothing that this could resist that way anyway. So that'll give you the F at C. Some moments about the X. Now, this is going to be such that it takes me a minute to look at this, but I don't see where this can't take a moment that way. This has a ball here. So to me, this three-dimensional structure has a bearing here welded to the ground. If I look back at the book, go back a section or two, and yeah, let's look at from the table of contents view. Okay, as I roll down through this and look at these supports, I see a journal bearing able to carry this. Okay, so that's me. Oh, it won't allow me to do that. Let's do this. So as I see this problem, I see a journal bearing without looking at the actual description. Let's give it a few minutes to come up, and we're going to look at it. Okay. Okay, determine the component of the reaction that the ball and socket joint at A and the smooth journal bearing at B and the roller support at C exert on the rod in 528A. I don't agree with this. It would be okay until he's summing the moments about Z. So, he's made an assumption that it's not going to carry a moment when clearly it states that a single journal bearing can carry a moment perpendicular to that line of action there. So what's the best way to think about this? I don't know. If it's nebulous like that, I would always add a constraint that fits the reality of the situation. He did not in this problem. So just be forewarned as you go forward. Not everything is perfect. Let me look at the next one. Here's a fairly simple one. This is almost like what you've seen before. you've got the reaction at O. You can only carry, there's no moments that can be carried there. And so what he does, he basically solves FAB and AC. And he does the sum of the moments about the O to determine, okay, wait, FA, FC. He does R across that. Let's see if I can move that out of the way. Whoops. Oh, here we go. We end up with this. When you're doing this R cross F and you have this embedded in here is three specific equations. One that has an I on the term, one that has the J on the term, and one that has the K on the term. So you can break them all out and you can find this. Now, the other way to solve this, so what he's done here is he's summed the moments here, looking out here and finding his equations here to find these two. Here's a situation where your reactions here, and here, these are straightforward. They can only be in tension, They can carry three different loads, but it looks like a ball joint, so it can carry no moments. And that's what you get. Equations of equilibrium. You could take this one, do some moments about this. That should give you enough to solve those two. What he's done is list all these. He did his sum of the forces first. And then he did the sum of the moments, the R crossed. So he did RC cross F. Why did he do that? Because he drew a vector from here to here, crossed it. Then he's going to draw a vector from here to B. And so that's what he does next. Crossed it with those two. You end up with a set of equations which were broken by component I, the J, and the K. Give you three equations, and you can solve them all to get that. So I don't know what the extra drawing is there for. So let's go ahead and try to find a problem back there that all right. Okay. So he has some of these worked. I think the next thing is fundamental problems. Let's take a look at those. We may just pick up one of those and work it. No, those are all worked for you. Except maybe some of these. A, B, and C of the pipe assembly. Okay, I think there's enough information. I can just do this. Oh, wait, I already had this thing out. let's go ahead. Okay, so we're going to drop our problem there. Then I'm going to go down and possibly work off this, or in order to save myself some work there, I may put the free body forces right on there. Well, first of all, I can carry this. This would be, I'll call it CZ. I cannot carry a load like that. It'll just slide through there. But I can carry one that's this way. And one of the things I'm going to do most of the time is I'm going to line up the arrows in the direction of the coordinates. What type of moment can I carry here? Well, first of all, I really can't carry a moment around that axis being the one here. I can't twist around that. And so that's going to be gone. I can, however, twist it about this axis. In other words, I'll call it moment, or MC about Y. And I should be able to take a moment here. However, he may not like you to do this, even though the moment about the C, this would be about Z. You can carry that. So I'm purposely causing problems here. Okay, this can carry a reaction here. And I'm going to look at what he has back there in a second. I can carry a reaction here. This would be BX. This would be BZ. I'm going to be kind of cramped here. So the question is, can I take a twisting moment like so? The moment at point B in the direction of Z, can I take a moment here? The answer to that question is no, because it allows the bearing to slide around. Can I take a moment about here? Technically, yes. The X, meaning that I can twist this way. In other words, if I twisted this way, would the thing hold against it? Technically, yes. And this last one would be a Y. Can I take a load this way? No, I can't. It'll slide right out of the journal part. Can I take a load this way? Yes, I can. AZ. Can I take a twisting moment here? Meaning that I would twist it that way. In other words, if I sliced everything off, put a load out here, would this bearing hold it? The way it's designed, the way these things are talked about, back right here, the answer to that question is yes. So this would be a moment A and the Y. Can this take a twisting this way? Technically, yes. Meaning it would twist around there. So if you count this, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Got 12 unknowns. I got too many. So the first thing I'm going to look at is, did he do this again? Because if he did, that's not actually the way to do this. So let's take a look. F10, F510, and what we're going to do, okay, I'm not getting much speed here. Interesting. I don't know what happened there. Oh. All right, let's take a look. F5, 10. Did he do this? Believe it or not, I think he did that again. So this is the part that you've got to do for yourself, in the sense that he's telling you one thing, but you're looking at something different. I contend that that's completely wrong. Let's take a look at what he actually is doing. What? Okay. Where? Okay. Where was I? F5-10. What the heck? Okay, wait. Very annoying. Okay. Yes. To me, totally incorrect. So he is teaching you something totally incorrect. Let me redraw this in the way that he intends to do it. but does not actually do it. Okay. Okay, well, I've already got a copy of that. So let me just do edit. Let's do a copy. I'm going to go over here. So this is what he's given you. This is what he's solving. Let me try to work this out. Okay. What he's actually solving is this. I'm going to do something. Okay, hang on. So what he is actually doing is he's doing something along these lines. He's taken this support, dropped it down into the point where it's sitting in a ball joint. So in other words, the piece is coming out. Here's a part right here. It's in a sleeve. It's very annoying what he's done here. Here, let's do it. Try this again. Here's your sleeve that it's sitting in. He is taking the sleeve, made it go down into a bar in which a ball sits there and is welded somehow to the bottom of this. And that ball is placed in a joint here. That is the only way you can do this to actually get the loads that he's prescribing. If you take this and you put a bearing just like this, and I take this shaft and twist it this way, this bearing will give back a resistance to that moment. So in fact, his drawings are inconsistent. His assumption that each of these terms are non-existent is incorrect for the drawing that he's given you. So he's assumed all these blue parameters are not there. In other words, there's zero. The only way you can get that with a bearing is if it's a ball bearing, so to speak. He's already taken you across here. I'm trying to explain this so that you're not. This is what he says right there. He shows you in clear present view that in fact it can carry a moment. This thing can carry a moment. He shows it carrying a moment. The moment's being carried right there. It's right there. Very plain to see right down here at the bottom. Then he gives you a problem that contradicts that completely. Not only that, he works one in the solution that includes no moment. So I'm telling you, and I would believe that anyone would back me up, that if you don't want that member to take a moment, the only way to have that happen is if this thing sat in some sort of ball bearing here so that this thing could rock back and forth. That's an improper constraint to begin with. So if he's given you this in that analysis, that's a completely wrong way of doing things. I hate to burst your bubble, but if you look at it close enough, Um, you'll see that contradiction. Unfortunately, we still have to progress on. Very annoying. Now, these are straightforward. Now, let's see what he does with this one. F512. This will be interesting. I'm going to go ahead and grab this one. And we'll see if he does this. Let's see what he does with F512. Okay. I don't know where he's doing this, but very annoying. Let's go in and look at some problems that are in the. So he's done the same thing on this one. Now, he can get away with that. Okay. All right. All right. So let's see where. Okay. So let's go in here. Let's go ahead and pick up a problem that is a legitimate problem. All right. Looking for something interesting. Okay, so I just had to place some interesting constraints on this one. This is good. I like that. That's interesting. Um, I don't know how to get rid of this. How do you get rid of it? Okay. All right, here we go. Whoops. I saw the problem below it. It looked more interesting. That one I would stay away from because he's done that. He's already shown that he's not willing to put the loads on there that he himself said were there. Um, let's set this one up and we'll finish it. Save later. So I never solved that problem because it has an ill constraint. Uh, all right, so let's put, first thing we'll do is we'll put the loads on there. Obviously, the first load is, I'm going to have a tension here. I'll deal with that later. The second load is, I'm going to have some sort of force here, which okay, it says determine the components of the reactions of these supports if the cylinder has a mass of 40 kilograms. So this load will be 40 times 9.81, and we'll figure that out in a little bit. Okay, so what type of force can this thing produce? Okay, he does have this. These are the same bearing forces, but he's put these across from each other. And I guess, okay, and we'll come back to this next time, I think. If you think about the type of bearings, that one support really does bother me. In this case, there is not that problem here. One, this thing can hold a load in that direction, so I'll call it A. And actually, since X is going the other way, I'm going to reverse it and say AX. Can it carry a load in this direction? No, it can't. Can it carry a load in that direction? Yes, it can. Now, can it carry a moment about this? In other words, draw this vector in that direction, take your thumb and point it in that direction, rotate your fingers, and that's what you get. So you get the moment at A in the X direction. Whoops. In the X direction. Yeah, I think we can do that. Can you carry a moment here? Moment A in the Y direction. No, you can't carry one that way. Can you carry a moment this way? M A in the Z direction. Yeah, you can do that. So you can do all three of those. Okay, so now that we've got all three of those, let's see what we can do next. Okay, I'm trying to find. All right, so you have this structure with all of these on there. I'll call this tension CB. Okay, so what we have, sum of the forces in the X direction equaling to 0. If I run out the X direction, all I get is AX. And then I get a component of this vector in the X direction. If I really look at it, I'll say, okay, what is TCB? What is that as a vector, well, it's equal to the tension CB times a unit vector that goes from C to B, which actually, if you go from R from C to B, it would be a vector that would, I'll just run it using different color here. I'll run it from here to here, back to here, up to here, and over and across. And that's the vector I'm going to be, that's the point where I'm going to want to end this. So if I'm running down the X, I'm running a minus 3 meters down that. If you're looking at it, I'm running it down the Y 1 meter here and a half a meter there. And the Z, I'm running it up 1 meter in the Z. Now, let's look. R CB is equal to minus 3 minus 1.5 and 1. U CB is equal to RCB divided by the norm of RCB. Okay. Which is essentially going to be minus 0.85714I minus 0.42857J to 81K. Okay. So as I sum the forces in the X here, I have, of course, this one, but I also have a portion of that one minus T CB 0.85714. Okay, if I sum the forces and the Y equals 0, I may end this in a second and pick this up in a minute. Let's do Z first. Z be AZ minus, oh, we're getting close to the end anyway, and I got to start the other, so I may finish this up next time.